Partial derivatives are a way to in a sense, take the derivative of a function of several variables, right? With a function of one variable, obviously you guys are at least familiar with how to take the derivative. You just take the derivative with respect to whatever variable that function is using. But if like we just saw, before spring break, we have a function of several variables, it's hard to think of taking the derivative with respect to several variables at a time, so we don't. What we do is we take partial derivatives, which are just, which just means take the derivative of the function with respect to one of the variables at a time. Now, what's going to happen to the other variables is they're going to be thought of as constants. Okay. Yeah, and this process is called partial differentiation. What you end up with is the partial derivative. Okay. And you don't have to pay attention to these formulas. Just know that. So you don't have to pay attention to these. Like we're not going to use the limit definition here. We're not. But what this is basically saying is that f sub x with this little x here. Just note that that's right there. That's with respect to x. That's the derivative with respect to x. So y is not changing, but x is changing by a little bit, and you're measuring the difference in the function based on that little change in x. So you're taking the derivative with respect to x. Here it's just the opposite. Here x is being held constant, and y is changing a little bit. So this is the partial derivative with respect to y. And this will be easier to see once you're actually doing it. But the idea is that one of the variables is held constant, the other one is allowed to change, and you measure the change in the function with respect to whichever variable is changing. Okay. Alright, so we will take this function and find the partial derivative with respect to x and, not this, but this. Yeah, we'll take this and take the partial derivative with respect to x and then with respect to y. Okay. So this looks like a complicated function, but partial differentiation actually simplifies this process quite a bit. So let's say we're looking for the partial derivative with respect to x. Now that's going to be denoted with a little f, with a regular sized f, but then a little x as a sort of subscript to that. This is the partial derivative with respect to x. Okay. So what this means is y is a constant, or it is constant. Or consider y to be a constant. Okay. So that means this. Let's see. Yeah, that's green. Okay. Consider this y squared to be a constant, and this y to be a constant. Just the same as if it were k or a or b or c. So this is really just a polynomial in terms of x. If you want, what you can do is you can explicitly just say, you don't have to do this, but it's an option. You can say, I'm just going to call that c squared. And I'm just going to call it c, if that makes it easier to envision. Or you can use k or a or b, if it's not easy for you to think of the letter y as being a constant. But the derivative of 3x is 3. The derivative of minus x squared times a constant is going to be minus 2x times that constant. Again, you can just write y squared if you're not changing it. But but then the derivative of plus 2x cubed, that should be plus 6x squared times that constant that you had. So
why didn't we take the derivative for y?
Because we're holding y constant. Y is just like 7 or
Okay,
8.
The constant doesn't.
Yeah, the constant it's a constant multiple. It just sort of stays there as you differentiate. Yeah. Of course, if there's a constant by itself, the derivative is 0. But if it's a constant multiple, it sort of carries on. Yeah. So this is really what, 2x y squared plus 6x squared y. Yeah. If and of course you'll have that if you never actually changed it to BC or whatever. This is just something you can do. I'm not going to keep doing it, but it's just an option. So this is the partial derivative with respect to x. Okay.
So now we need to do the same with respect to x?
Or with respect to y, yeah. Holding x constant, yeah. So fy, partial derivative with respect to y of this function. I'm just going to get rid of this. Just, you guys know you can do it. All right, and here, with the partial derivative with respect to y, we'll consider x to be a constant. Consider x. Okay. So if x is a constant, that means the derivative of this first term, 3x, is, 3x is a completely constant then. Then the derivative of that is 0.
So it would be,
Yeah, x is a constant. Same as if that term were just 27 or 42 or, the derivative of it would be 0. Since it is a constant.
Right.
Yeah.
Why don't we take 0 for y squared and not there?
Because with these, their y squared is being multiplied by some kind of x. Yeah, it's a constant multiple, not just a constant term all by itself, like the 3 x's here. Yeah. Okay. This we'll consider okay. Now we're considering x to be a constant. So this is a constant, this is a constant, this here is a constant. Okay. So this term is all constant. This middle term here, we have minus a constant times y squared. And we're only taking the derivative with respect to y. So we'll have minus 2y times that constant. That just sort of stays. Okay. And this last term, 2x cubed y, x cubed is a constant. All we have is it is 2x cubed because the derivative of 2y is just 2. And we still have that x cubed sort of just hanging around because it's a constant in this case. So what we have is negative 2, I guess if you wanted to reorder it to be all nice, negative 2x squared y plus 2x cubed. So yeah, the partial derivative with respect to x and with respect to y are generally going to be pretty different from one another because there are very few functions that are exactly symmetric with respect to x and y. most usually contain some sort of mix. Oh, what's up?
This is like 3x.
No, x is a constant. 3 times a constant is just a constant. The derivative of a constant is 0.
Oh.
Yeah.
Te hubiera ignorado porque hubiera saludado.
¿Cómo lo pasaste?
Bien. El Enrique, yo te vi jugando también. Verás. Porque yo llegué a la parte. No, mira. Yo más adelante está la parte final, solo para explorar.
Alright.
Y los centros y yo dije, no, pero no pasa mucho. Aunque ya lo platico de antes.
3 minus 2x. 3 minus 2x squared. Yeah, okay, cool. Alright.
Related to what is now available.
Wait, what? Okay. Alright, so that's those are the 2 partial derivatives that we got. The partial derivative with respect to x and the partial derivative with respect to y. Let's see. I really should say f of x comma y. Okay. Alright, there should be an f in front of this. Okay. So, boy. Alright. So to find the partial derivative with respect to x, so f, little x of x and y. Okay. Now with respect to x, this y is a constant. With respect to x, this is a product of 2 functions of x, so you have to use the product rule. And very likely inside of that product rule there's going to be some chain rule, maybe. Okay.
Are you gonna get us an exam or something like this?
Yeah, I don't think, not with this many layers. Okay.
I mean, we're in count 3, bro. I would anticipate.
No.
It's literally just derivatives. Like, we just got done with count 2.
Yeah, I know, but
Invite this one for me. No,
so breaking it down real simple. A is ln of x, the natural log, the derivative of which is 1 over x. B we can consider to be sine of x squared y, of which the derivative with respect to x, because we're doing the partial derivative with respect to x, should be cosine of the same times, because of the chain rule, the derivative of the inside with respect to x. So that is times 2xy. Got to keep sort of remembering to be taking any derivative that you're taking with respect to x when you're taking the partial derivative with respect to x. Right? 2xy, because that's the derivative of x squared y with respect to x. So that's because y is constant. Okay. So actually, this is all that you need. You just put this together. So So the partial derivative with respect to x should be, a with b prime and a prime with b. So the natural log of x times cosine of x squared y times 2xy. And I'm sure there's like a better way to like order those things, but the order doesn't really matter. Plus the other two. 1 over x times sine of x squared y. That's it. That's the partial derivative with respect to x. I mean, all the derivatives that you need to take, you take during, when you lay out the product rule. If you sort of do it that way, sort of off to the side. Right now, the derivative with respect to y is much, much easier. Because if you might notice that not both both these functions have x, but only one of these functions has y. So the natural log of x. So when you're taking the partial derivative with respect to y, the natural log of x is a constant. Okay. Right, here's the f that's missing. It's actually very, very simple. The natural log of x is so this is a constant, this is a constant. So we're basically taking the derivative of sine with some, constants being multiplied there. So the natural log of x is just hanging out as a constant. The derivative of sine is cosine of the same. And because of the chain rule, you got to take the derivative of the inside as well. With respect to y this time, you have that constant x squared in there, but the derivative of a constant times y, the y sort of just differentiates it to 1. So what you're going to be multiplying by in the end is x squared. Same as if you had 3y, you'd be multiplying by 3 at the end. Or 42y, you'd be multiplying by 42 at the end. The x squared is just a constant that y is being multiplied by there. So when you take the derivative of a constant times y, your result, that derivative is just that constant that you had.
How would the question be asked?
Find the partial derivative of this thing with respect to x or with respect to y. Yeah. So these are all the same, like, sort of elementary derivative rules that you already know, but you have to actually almost like ignore what you're seeing, like with one variable or the other, and just sort of pretend like you don't see that it's a variable, like pretend like it's a constant, and just treat the function as if it were a function of only the one variable. Alright, get that right. Yeah, cool. Alright. Okay, so we've been using this notation for partial derivatives so far, like, the same f, but with a little x or a little y in, as a subscript. It's possible that you might see other notations for a partial derivative. Most notably, something analogous to the dy dx that you might have seen before, or that you definitely did see before. Okay. So we've seen so far f with a little x in the corner, f with a little y in the corner. How you might also see that is, assuming that you're calling the function z, that that your function of x and y is going to become your z. This is a lowercase delta. Yeah.
What is the name?
Well, it is a lowercase delta. Is what the letter is, but how this is said is usually del z del x.
Okay.
As opposed to like dz dx, it's del z del x. Yeah. But it denotes a partial derivative, where d is usually reserved for like functions of a single variable and like an actual like total derivative. This little lowercase delta is used for a partial derivative. And same thing, if you have the partial derivative with respect to y, it's del z del y. If you find the partial derivative and you proceed to plug in a point, I mean, you're probably familiar with this notation anyways. It's like the derivative with the evaluation bar, and it tells you the point to plug in. Or, you might just have like the function notation with the little x or the little y in the corner. It tells you to plug in that point. That one's not nearly as important. Okay. But, you might see the sort of function notation with the f and the little letter in the corner, or you might see the sort of delta notation. Both just mean the same thing. The whatever variable is on the bottom, that's the variable that the partial derivative is being taken with respect to. Anything else that's not that variable is treated as a constant. Okay. What a partial derivative is, or like how to interpret a partial derivative, is basically what is the slope if you're going only in the x direction, if you're talking about the partial derivative with respect to x? Or what's the slope of the line on the surface if you're going only in the y direction, if you're talking about the partial derivative with respect to y? So this is the partial derivative with respect to x, and it's the slope if you're only looking at the x direction. So assuming that, because...
So these partial derivatives represent the direction of the slope, pretty much.
Yeah, the slope when you take it in a particular direction.
Okay.
Yeah, because if you imagine, I don't know what's a good surface here. Here. So imagine we have a surface like this. Now at this point right here that I'm pointing to, if you took there are a lot of ways you can think of the derivative, because if you measure it this way, it appears to be increasing, right?
Yeah.
Yeah, it's going up.
Mm-hmm.
But if the point's not going to change. But if I measure it in a different direction, that is flat.
Right.
Yeah. So let's say that okay. So let's say that the x-axis is going this way and the y-axis is going this way.
Okay.
The partial derivative with respect to x will be 0. But the partial derivative with respect to y will be increasing.
Right.
Yeah. So it's like you're just sort of taking, you're measuring the slope in a specific direction, either in the y direction or in the x direction. Yeah.
Okay.
So that's what these partial derivatives are for. Yeah. So if the surface here is in red, just sort of you don't have to pay too much attention to the blue plane here, but the plane is just saying y is constant. It's not going to move in the y direction at all. It's only moving in the sort of x direction. If you were to measure the partial derivative at this point, the partial derivative with respect to x, so only in the x direction, as x increases, this appears to go down. So the partial derivative with respect to x at this particular point would be negative. It's going down as x increases. If you were to measure it in the other direction, if you were to measure the partial derivative with respect to y, well, it would probably look more like, sort of looking at it here, it would probably form a line like this, sort of. And it would also be negative if you take the partial derivative with respect to y. It's also going down sort of as y increases. Like if you only pay attention to the y and assume x is constant. So it's, in a way, a partial derivative is sort of like, limiting your view of a three-dimensional surface, assuming that one of your variables is constant and only looking at one of the variables at a time. Yeah, all right. Hold on. Oh, well, there you go. That's your slope in the, this would be the partial derivative with respect to y. X is some sort of constant, and so, you're only looking at the change in height with respect to the change in y. You're not paying attention to any, there's no change in x, so you're only trying to measure the change in the function with respect to y when you take the partial derivative with respect to y. So yeah, they're basically the slopes in the x direction or the slope in the y direction for the partial derivative with respect to x and the partial derivative with respect to y, respectively. So just, if you're going only in the x direction, the partial derivative of f with respect to x will give you, that slope. If you're going only in the y direction, partial derivative with respect to y will give you that slope. All right. So this seems like it might be a new question, but it's actually not. Slopes in the x direction and in the y direction, it's going to be the partial derivative with respect to x at the point. And this is going to be the partial derivative with respect to y at the point. And it gives you the point. So, but first, to have something to plug this point into, we got to find the actual, we got to find the expression for these partial derivatives. So, partial derivative with respect to x is, well, the only x is here, so the derivative of, with respect to x of negative x squared over 2, throw that 2 in the front, that's going to cancel out with that 2 on the bottom, and you will have negative x. With respect to x, at least, this middle term and this last term are constant, so they go away. Yeah. Now the partial derivative with respect to y this is the only y term. So the derivative of negative y squared is negative 2y. The first term and the last term contain no y's and so are constant, and the derivative with respect to y of those is nothing. So these are actually pretty simple first partial derivatives. And if you go ahead and plug in your point, this is your x, this is your y, this just happens to be your z. It doesn't get plugged in. That's just what the function is if you plug in 1/2 for x and 1 for y.
You don't have to put the y constant anymore?
Well, you can. Y is constant here, and x is constant here.
But that doesn't really matter. Like we're not interested in it for this problem.
We're doing this the same as the previous problems. The difference that you're seeing might be because in the previous problem, there were terms that were mixes of x and y. Yeah, whereas with these, the sort of x term is just by itself, like x by itself, and this is a term with y by itself, and so they don't really, they're not.
They're like, okay.
Yeah.
They're like constant.
Right.
Yeah, the second one is pretty much 0 times y squared, so you remove it.
But there's not another variable attached to it.
Yeah, exactly.
Yeah, if we sort of go back a little bit, for this one there were mixes of x and y, and so some of you treat them like constant multiples instead of like constant terms, and so they tended to carry on to when you had the partial derivative. Same thing here. There are terms that are mixes of x and y, and so some of the constants will tend to carry on when you take the derivative.
They're not like numbers. But, I mean, they're not really numbers, but like we treat them.
You treat them like they're constant numbers. You sort of bring them down as if they're attached to something that you can actually, yeah. If they're just by themselves and you're treating them like a constant, they go away completely. Yeah. And that's the case here. They are, these are x terms sort of just x by themselves. There's a y term sort of by itself. Yeah.
That makes sense.
Mm-hmm. Okay, so
-1.
yes, yeah. So what you're doing is you're plugging in 1/2 for 1/2 for x and 1 for y. Although y doesn't really factor into this one, but you end up with -1/2. Whereas with partial derivative with respect to f, with respect to y, partial derivative of f with respect to y, you plug in x and y into that. The x doesn't really matter, but you plug in 1 for 1 for your y, and you end up with a value of the partial derivative of -2. Now there are partial derivatives that you might have to use both of them for, but for this problem in particular, it was a pretty simple partial derivative. They just contain one variable. Okay, so what this means is that this is the slope in the x direction. And this is the slope in the y direction at that point. Now, how this surface looks, it's basically z equals -x squared, -y squared. It's going to be an upside down paraboloid, which is it just sort of means it's like a parabola in both the x and the y direction, and it all sort of comes together into this sort of weird rounded parabola shape. But we're gonna see a picture of that. So this is the paraboloid. It's only a picture of it in the first quadrant. Like it extends past this, but there's no need to see that. So this is the point we're looking at. So this is the point we're looking at, 1/2, 1, 2, and this is the slope in the x direction, because this is the partial derivative with respect to x. And so if at this point you were only measuring how the slope changes in that x direction, you'd measure a value of -1/2. That's just the slope. As you move 1 unit in the x direction, the height decreases by 1/2, just at that moment. And if instead you took the partial derivative in the y direction and you were only measuring the slope in the y direction, you'd get a steeper drop at that same point. A drop, basically a slope of -2. So these are the same point, you're just taking the derivative in 2 different directions. If you take it in the x direction, if you measure the slope in the x direction, you get a value of -1/2. If you measure the slope in the y direction, you get a slope of -2. But that's what these partial derivatives are. They are the values of slopes, or they're formulas for the values of slopes taken in a particular sort of direction, a particular orientation. All right. So you can extend this to honestly functions of any number of variables that you want, and it's not going to be any harder, because when you take a partial derivative, you only consider one variable and consider, sort of assume literally everything else to be a constant. So no matter how many variables you have, just because the process of taking a partial derivative, is that way, where you're only considering one variable at a time, it actually doesn't get harder. It doesn't get that much harder when you add in more variables than that. Yeah, so still, consider one variable at a time. Anything else that's not that variable is a constant. Yeah, again, you don't have to really pay attention to this stuff, but, because we're not going to use the limit definition. But let's say that we had a function that used all 3 of x, y, and z as inputs, and assigned it to a 4th variable, w. That might be a function that takes three variables as an input might be something like, the density of a block of material, if it's more dense in some places than others. Then you have an x, y, and a z for your location, then w is going to give, as a function, it's going to give, the density at that point. Or the temperature in a room. You have an x, y, z to describe your location, and then the 4th variable w describes whether it's cool or hot at that location. Just an example of a function of 3 variables. But you treat it exactly the same. You do the exact same process. Only consider one variable at a time. Everything else is constant. Okay. Let's take the derivative of this with the partial derivative of this, rather, with respect to z. That means we only consider z, and everything else is a constant. Everything else that's not z is a constant. X, y are constants when we take the partial derivative with respect to z. So So x and y are constants, which means this first term is just a constant term, so the derivative of that should be 0. Y is a constant. That means that it just sort of stays as a constant multiple, but the derivative of yeah, I'll have to sort of rewrite this. Okay, which means we only consider the z squared, and we only derive the z squared, which means that we get 2z times that y from before. And last, the derivative of z is 1 times that constant multiple of x, so that's just x. So in a nicer way, the partial derivative with respect to z should be 2yz plus x. We'll take the derivative of this with respect to z as well. Okay. And if you want, you can, find the partial derivative of these with respect to x and y. That's fine too. But just in this instance, we're looking for the partial derivative with respect to z. So again, x and y are assumed to be constants, which means that this is a constant, this is a constant. Yeah. So this is actually a product rule. You got one function of z, which is z, times another function of z, which is sine of xy squared plus 2z. Okay, so this requires the product rule. Our first thing is z, the derivative of which is 1. When we take the derivative with respect to z as we are doing. The other thing, our b, is sine of xy squared plus 2z. The derivative of which is, of course, the derivative of sine is cosine, and we keep the inside the same. It's xy squared plus 2z. But then because of the chain rule, we have to multiply by the derivative of the inside. The derivative with respect to z, of course. The derivative with respect to z of the inside.
At the beginning, do we need to put the b prime or just?
Oh shit. Yeah, there should be a prime on that b. Yeah. Xy squared is a constant. The derivative of that part of the inside is nothing. The only thing you actually get to take the derivative of is 2z, which the derivative of that is 2. So multiply by 2. Okay, now sort of put this all together. A goes with b prime. A prime goes with b. And so the partial derivative with respect to z is z times cosine of all this stuff. Nope, xy squared, okay, plus 2z times 2 plus 1 times sine of xy squared plus 2z. If you really wanted to, you could reorder the terms to clean it up a little bit. Generally speaking, when you're dealing with a combination of things, the constants go in the very beginning, then the purely algebraic stuff, then the trigonometric factors. So the actual process of finding the derivative is no more. It's no more difficult than if this x and this y squared were literally just like 7 and 113. You know, it operates exactly the same way. You just have to sort of ignore your gut impulse to think of them as variables and just think of them as constants instead. I mean, that's probably the hardest part of this is to ignore, you know, the impulse to think of them as variables, and instead to think of them as constants. Okay, all right. Yeah. Okay, all right. Okay. We'll take the partial derivative of a function that has 4 variables in it. But you're also going to find that it's no harder than if there were only 2 variables. Because everything aside from that is, you know, everything aside from the variable in question is a constant. So we're looking for the partial derivative with respect to w in this case, of this function of 4 variables, x, y, z, w. I don't know what letter gets used after w if you wanted to call this some sort of letter, but okay. So since we're taking the partial derivative with respect to w, that means that x, y, and z are constant. So that x, y, and z on the top, that, you know, those are as good as, you know, 1, 2, and 3, or 10, 17, and -5. You know, might as well be those. W is the only thing that's actually considered a variable here. And so, if you remember the power rule, this is actually x times w to the -1. And again, this is a constant. So the derivative with respect to w, well, it's just the power rule. You take that -1, you throw it in front, decrease the power by 1, and then that constant was there, so it just sort of gets to stay along for the ride as w actually does the work of changing, you know, taking the derivative of. So if you wanted to rewrite it, you could send that w to the -2 to the bottom as w squared, while the x plus y plus z stays on the top. So yeah, just literally ignore part of what you're seeing. You know.
What's the point of taking partial derivative?
They let you know the slope just in a particular direction. That's basically it. Yeah. And in particular, because, like, you know, in calculus 2 and calculus 1, when you were talking about functions of a single variable, where, like, you know, y equals f of x, it's easy to get a single value for a derivative. Whereas in 3 dimensions, I'm just going to pull this out again. It's not as easy because you don't know because the derivative is going to be different based on what direction you're going in. So these partial derivatives let you know that, you know, okay, well, I'm measuring this going in the x direction, or I'm measuring this going in the y direction. Because without specifying, there's not, you know, a surface doesn't have a single value of a derivative at any particular point. It's going to depend on what direction you're going in for 3 dimensions. Yeah. Okay. And the last thing we're going to talk about is higher order partial derivatives, which, just like taking the second derivative of something, in calculus 2 or calculus 1, just means that you do this process sort of again. Okay, but we'll get used to the notation first. All right. So you're definitely much more likely to see, for example, this sort of notation for when you're taking the higher order partial derivatives with this little f. And so with this function notation, I guess when you take the partial derivative with respect to x twice, you're just doing it with the same variable both, but 2 times. Same thing here. But I just want to specify that when you're taking the partial derivative with respect to 2 different variables, one after the other, the order can matter. It doesn't always, but it can. And so you want to be sure that you're sort of interpreting this correctly, interpreting this correctly. And so with the function notation, the order of partial derivatives that you're taking with the function notation is, you just sort of read it from left to right. So f sub xy means you're taking the partial derivative with respect to x first, and then the partial derivative after that with respect to y, second. If you happen upon this notation, that is the opposite. The one closer to the right is the one you do first. It's the one on the inside, that you do first in this notation. So just know that that's backwards if you see this notation, right? So in both these cases, you're taking the partial derivative with respect to x first, and then with the partial derivative with respect to y. With this del notation, that x that comes first, that's going to be on the right-hand side because it's like on the inside of this thing. Whereas with the function notation with a little subscript letters, you just read that normal. But basically, just know that the order matters, and you're mostly going to be seeing the function notation with the f and the little letters, so you would just read that normally. This is just, the other order. First with respect to y, and then with respect to x. So again, the function notation you're going to read from left to right. The del notation you would do whatever's on the right first and move left. So the third and fourth cases here, where it's x and y together, are known as mixed partial derivatives. Mixed because literally the variable that you're taking partial derivatives with respect to, you're doing a mix of both. Whereas the first two here, the first one is purely with respect to x, just twice, and the second one is purely with respect to y, just twice. Okay. All right. So there are multiple second partial derivatives, as you saw. In fact, there are liable to be as many as 4. Okay. Yeah, sure. So if you're talking about first partial derivatives, you can have, 2 either. Assuming that you're starting with a function of x and y, your first partial derivatives, there'll be two of them. One with respect to x and one with respect to y. When you talk about second partial derivatives, there are now four. xx, xy, yy, and yx. If you were to, for some reason, to start going into the third partial derivatives, there'd be 8. If you went into fourth partial derivatives, there'd be 16, then 32, then 64. But we don't really ever go that far. No. Okay. So before you find the second partial derivatives, you have to find the first partial derivatives. So actually, we do this. Okay. So we're going to be looking at the first partial derivatives to begin with. And so this is f, and we're going to look at the partial derivative with respect to x. So here, I'm sure you guys know by now, but y is constant when we take the partial derivative with respect to x. Okay. Y is a constant. That means that for this first term, y squared is a constant, and so really we're just taking the derivative of x, which is 1. So that first term is going to end up as 3y squared. This middle term is going to be nothing, because y is constant, yeah. So I guess plus 0 if you wanted. And this last term, again, you're only taking the derivative with respect to y. So the derivative, you're only taking the derivative with respect to x, yeah. So the derivative of 5x squared, that's 10x. And that y squared is just sort of there. So the partial derivative with respect to x is 3y squared plus 10x y squared. Now if you were to do the same for y, you're going to hold x constant. And looking at that again, x is constant this time. So with this first term, what you're taking the derivative of is y squared. That's going to be 2y. And everything that's multiplied, everything that it's being multiplied by is just going to go with it. So that'll be, 6xy? Right, that 2 goes to the front, becomes a 6. Y gets its power decreased by 1, so 6xy. The derivative of minus 2y with respect to y is minus 2. And again, we're taking the derivative with respect to y. X is a constant, so this x squared is just hanging out. We take the derivative of y squared, we get, we take 2 to the front. So that's 10. X squared is just sort of there. And y gets power decreased by 1. So that is, that partial derivative is a little bit more, because the middle term didn't go away like it did last time. But there it is. 6xy minus 2 plus 10x squared y. Okay, so those are the first partial derivatives. So these are the first partial derivatives. Now if we want to find the second partial derivatives, we just take the partial derivative of these with respect to x or with respect to y. Thankfully, generally speaking, the functions that you see, that you have to do this partial derivative stuff with respect to tend to be polynomial, which means they get simpler as you take the derivatives, not more complicated. So from this, we're going to get fxx and fxy. Okay. Now the derivative of this with respect to x, meaning everything else is a constant, everything that's not x is a constant. This first term goes away completely. We take the derivative of the second term with respect to x. The x differentiates to a 1, and we get 10y squared. If we take the partial derivative of this, of f sub x, if we take the partial derivative of this first partial derivative with respect to y, that's going to be 6y plus 20xy. X is a constant for this one. So that's a mixed partial derivative that we have there. On the other side,
So for the next partial derivative,
you take this first partial derivative, this one that's with respect to x, and then with this you take the derivative with respect to y.
So the first one is with respect to x.
Yeah, so the first one is with respect to x, which is how we got here in the first place. So this is not the original function. This is the first partial derivative with respect to x.
Okay.
Yeah. Yeah.
I think I get it.
Yeah.
Second time, right? It's in respect.
Yeah. You do it with x the first time, and then after that you do it with respect to y. Yeah. The original function was back here. This 3xy squared minus 2y. Yeah. This was the original function. This is the first partial derivative with respect to x. If you then take the partial derivative of this with respect to y, this is what you'll get. Okay, so fyy. So the second partial derivative, we take the partial derivative with respect to y both times. We just start with this, but we take the derivative with respect to y. So this first term, y is going to integrate into 1. Y is going to differentiate into 1. You'll have 6x for your first term. Minus 2 is a constant. Goes away. Plus 10x squared y. Again, y differentiates into 1, and you're left with 10x squared. And this mixed partial derivative where, it's y first, then x. We just take the derivative of this, the partial derivative of this with respect to x now, because, this is the partial derivative with respect to y. We then take the partial derivative with respect to x, we'll get this mixed derivative that we want. So with respect to x, 6xy, okay, well the x is going to differentiate into 1, leaving 6y. Again, minus 2 is going to just differentiate into nothing. Then 10x squared y, derivative with respect to x, that's going to be 20xy. Now notice something about both these mixed partial derivatives. Not always, but most of the time they will match. Yeah.
What is it? What is happening with the slope if it doesn't match?
It's not really anything to do with the slope. it has to do with its like continuity in the space, and it's a really complicated thing that makes them not match. But just know that most of the time they will match for these nice functions that are continuous everywhere. Yeah. Yes.
And just to clarify, the delta format puts out the exact same answers.
Yeah. Yeah, you'd be del z del squared z del x squared or something like that. Yeah, you'd just be using that instead of this. Yeah. Same sort of deal as f prime and dy dx. Yeah.
And you said we should anticipate seeing that one, or possibly.
I wouldn't discount it completely, but
Okay.
I hardly ever see it. Yeah. Oh yeah, right. And we were trying to find what the value of f of xy, f sub xy at -1, 2. Okay, so oh yeah, so we're trying to do this and evaluate at -1, 2. Yeah. Just 6 at 6 times 2 plus 20 times -1 times 2. That's 12 minus 40, -28. Okay. Yeah, that sounds about right.
We're going to have the same answer in the other side.
You would, yeah.
Just for the fx1.
Yeah. That's all we're really being asked to do. And kind of like with second derivatives that you knew before, these do, in a way, describe the curvature, just sort of in a kind of complicated way. In the same way that a surface can have different slopes based on like what direction you're taking the derivative in, they can also have different curvatures based on what direction you're taking the derivative in. You'll see it later, like we'll talk about them later. But there are these surfaces that I'm not even sure I can really draw it, but there are these surfaces that they curve down, measuring in, for example, the x direction, but they curve up, measuring in the y direction. We'll see some examples of those later. This is just, this isn't the actual picture of the function itself, but it's part of the motivation for why we'd want to, know this stuff. All right. Yeah. Okay. Yeah. If there are no discontinuities, open disk just means the sort of xy plane. Okay. But yeah. The mixed partial derivatives, like the mixed second partial derivatives, are going to equal. They're going to equal each other. As long as there are no weird discontinuities or anything like that happening. All right. Well,